Next, we move to example 2. Okay, so if you look at example number 2, we have two big questions. And then under question B, you have another small question, two small questions. Okay, so for the first question, it is all about the theory part. So, okay, so let's discuss. Okay, discuss the criteria followed when selecting FIR and IIR filters for an application. Your discussion should focus on the cutoff frequency and the number of coefficients. So basically, your discussion should have your cutoff frequencies and about the number of coefficients. Okay, so based on our lecture, okay, I already gave you the difference between IIR and FIR filter. Okay, so you may use that information. Okay, so to answer this one, okay, let me give you. We use IIR filters only when the only requirements are sharp cutoff and high throughout, as IIR requires less coefficient than FIR. Thus, we need to select IIR filter if linear phase is not important. That is for the first part. Second discussion is we use FIR if the number of filter is not too large and little phase distortion is desired. If linearity is required, then we select FIR filter. Okay, next. For part B, okay, there is two sub-questions. Okay, so given you have the specification, so if you read through the question, the specification is basically for bandpass filter. So again, here, if you look, if the question didn't mention what type of filter you have to design, okay, from the given specification, you can actually predict what type of filter you have to design. Okay, so from the given specification, we have three conditions. Okay, so if you look at the specification, okay, so we have two conditions, which is referring to delta S. Why? Because of the values is approaching to zeros, and then one condition is on the pass band. Okay, so you know that there are two types of filter, which can be bandpass or bandstop. Okay, so for the first part, for the first question, okay, the question asks you to sketch the tolerance diagram. Okay, so you have to sketch the tolerance diagram of bandpass filter. Alright, so when you write down when you sketch the tolerance diagram, make sure don't forget to label your axis. Okay, so for your axis, okay, refer to your specification. Okay, in the specification you have modulus omega. Okay, why we have modulus omega? Because this condition is for causal bandpass, means your signal is right-sided signal. Okay, and then we have modulus H exponent j omega. So modulus H exponent j omega is referring to your y-axis. Okay. Okay, so now we are going to design your filter. Okay, so first we have our value, which is from 0 to 2 pi. From 0 to 0.2 pi. Okay, so it is from 0 approaching to 1 values, and then it will going up. So you have pass band part, so it will going down. So this time around is quite high. So we have this one is ours for 0.01. Okay, the range is from 0 to 0.2 pi. Next, our passband. Okay, better you use your ruler. Okay, I don't have a ruler, so I just assume. Okay, so first one is at 0.95, second magnitude is at 1.05, and then we have our second delta S, which is at 0.02. Okay, so don't forget to write down, this is our stop band. Okay, so we have our first delta S value, omega S value, which is 0.2 pi. Okay, next we have our first passband value, WP1, which is 0.3 pi. And then we have our second passband, and then we have our second stop band value, which is at 0.8 pi. Here is pi. So we are going to have two delta omega value. So first delta omega value is from here to here. So it is omega P1 minus omega S1. So delta omega 1 is equal to so next you have another delta omega value. Okay, so delta omega 2 equal to omega S, omega C. So we have two omega C value. So our first omega C value equal to 0.3 pi plus 0.2 pi, you divide by 2. So you will have 0.25 pi. Here you have 0.8 pi plus 0.7 pi, you divide by 2. So you're going to have 0.7 pi, 5 pi. So that's all for tolerance diagram. So if you look at this question, okay, you need to have your minimum stop band attenuation value. So in the question, it did mention about the minimum stop band attenuation value. So if you look at the minimum stop band attenuation value, you need to refer to table number 5. Okay, so before I move to that, okay, first step, what you have to do is, first you need to list down what is your omega P value, what is your omega S1 value, what is your omega P2 value, what is your omega S2 value. Okay, next, for you to determine what type of window type, you need to know what is your minimum stop band attenuation value. So if you look at the question, you have your minimum stop band attenuation value, which is 733.9. So basically, if you refer to table number 5, it is referring to Blackman window. Okay, Next, in table step number 3, you need to determine your delta omega. So you have 2 delta omega value, but for both it is 0.1 pi. Okay. Next, what you have to do is you need to determine your capital M value. So again, for you to determine your M value, you need to refer to table 5. Okay, so refer to transition band column and make sure you refer to Blackman window rows. Okay, so from Blackman windows, you know that delta omega equal to 5.56 pi over M. So from here, you know that your M is equal to 55.6. And again, you need to round off. So when you round off, it is not similar to max. Okay, so what you have to do is you need to choose the next highest number. So the next highest number of 55.6 is 56. Okay, so next you need to determine your capital N value. So capital N is 2m plus 1. So you will get 113. So next step, you need to determine what is your cutoff frequency value. So for bandpass filter, we have 2 cutoff frequency value, right? So we have WC1 and then we have WC2. So refer to your tolerance diagram. So from your tolerance diagram, you know that your first cutoff frequency is 0.25, your second cutoff frequency is 0.75. Okay, step number 6. Okay, you need to determine what is your HN. Okay, so for you to determine your HN, you need to refer to table number 6. Okay, you need to refer to what is your HDN. Okay, so your filter type is bandpass filter. So you are going to have 2 equations. One for when n equal to 0, another one is when n is not equal to 0. So please, when you look at table number 6 for bandpass and bandstop, okay, if you look at the equation, from the equation you find that, okay, we have 2f1 blah blah blah, the omega 1 minus 2f1 blah 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 omega 2. Okay, you see that equation. Okay, you see that symbol. Okay, so basically f1 is your fc1, f2 is your fc2, omega 1 is your omega c1, omega 2 is your omega c2. Okay, alright, so same goes to bandstop. Okay, if you look at the bandstop equation for when n not equal to 0, when n equal to 0, you can see this term f1, f2, omega 1 and omega 2. So same thing, f1, f2 is actually your cutoff frequency value, omega 1, omega 2 is actually omega c value. Okay, next you have to write down your Wn value, the Wn equation. Okay, so you have the function for Wn. So after that, okay, for you to determine Hn, okay, I advise you to write down a table. Okay, so in your table you should have Hdn, Wn, and then you should have your Hn. So how to get Hn? Hn is Hdn times Wn. Okay, so again, in this question, it didn't state. Okay, So basically, the objective of step number 6 is to find the filter coefficient. Okay, so in this question, it didn't state your coefficient values. Okay, if the question did state on the coefficient value, for example, n equal to 10, 11, 12. So you have to write down 10, 11, 12. But if the question didn't state your coefficient, so you have to use your default numbers. So your default numbers is 0, 1, 2. Okay, so what you have to do next is you just substitute all this value inside HDN and WN equation. And again, I want to emphasize, make sure your calculator mode must be in radian. Okay, so step number 7, you have to make a conclusion. Okay, so to done for example 2. Alright, so that's all for FIR filter design. So please, for FIR filter design, it is very straightforward. So I want to summarize again. For filter design, you need to solve 2 issues. One because of infinite time problem, another one is all about non-causal problem. So how to solve the infinite time problem? You need to do windowing. When I say windowing, means we are going to select the important information. So we are going to select the important information and then we do the windowing. But then we have another issue, which is actually all about the non-causal problem. So for the non-causal problem, you need to solve, okay, by doing the time shifting. So where to shift the signal? Okay, you have to remember the definition of causal. Causal means you have to shift the signal to the right. So means for you to solve non-causal issue, we need to shift the left-sided signal to the right. So what, in terms of what value? It is M value. Okay, so that's it. Very easy, right, for FIR filter design. So I hope you give a try. So if you have any problem, please contact me. Alright, so thank you, see you again.